All right, so the first section is called real numbers and their graphs. Something.
For the notes, there's two.
The one that says slides. Okay? If you don't pick the other one will have all the answers already. Pick slides so we can work on it together. So we're looking at real numbers and their graphs. Okay? We're going to have three objectives today. First, we're going to talk about graphing real numbers on a number line, which should be pretty much review for everybody. We're going to look at comparing values and characteristics of numbers, and then finding the absolute value. So as I mentioned earlier, this first chapter, a lot of it is going to be a bit of material that you've seen already, but I'm telling you now, it's probably going to be a little more complicated. We're going to do problems that are a little bit more complex than what you've seen. So just because you know what absolute value is, doesn't mean that it's going to be easy, because some of the problems we're going to do are going to make you think differently than you may have in your other classes. Okay? So it might be a little bit of review in the beginning for some. The first thing we want to look at is the number sets. Now, as you can see, we have the real numbers. There's also a set of numbers that is non-real numbers. Does anybody know what they're called? Imaginary. Very good. Good, David. Now, imaginary numbers are something that you may not have seen yet. Most people probably haven't seen yet. But we're going to get to imaginary numbers. And when we get to the end of chapter 5, we're going to start looking at where imaginary numbers come up.
Aren't they the numbers of 5 after 1?
Good. Very good.
What happens when you square root of 8?
Think about a square root, right? Like, what's the square root of 9? Everybody? 3, right? But if somebody said, what's the square root of negative 9? It's not negative 3, it's 3i. And we'll talk about that later in the year. It has to do with the fact that you can't find a number when multiplied by itself that gives you a negative answer. It's impossible. Take any number and square it. You always get a positive answer, don't you? Pick any number in your mind. Anything. Negative 9 squared, positive 81. Negative 4 squared, positive 16. So to do the reverse and try and find a square root of a negative number, it doesn't make any sense. Because you can't find two numbers when multiplied to give you a negative answer, assuming that they're the same number. So if you had like negative 9, sure, 3 times negative 3 is negative 9, but that's not what a square root is. So we'll get to that later in the year, so there's no need to even write that down yet. So we're going to look at the real number system first. Within the real number system, there's two major categories, and you can see what they are on the board, rational and irrational. Now, can somebody give me maybe an interpretation that they know of already of rational versus irrational? Has anyone seen what the differences are here?
So a rational number is one that ends, that's not the right word for it, but like decimal points just ends at one point.
Good, it terminates. That's the word you're looking for. Good. As opposed to?
Irrational numbers which don't terminate.
Okay, what do you mean they don't terminate? I need a little more.
Keep going on.
Without any what?
Without any.
What's the word you're looking for? Because the number, right, 1/3 as a decimal is 0.3333333. That goes on forever. But what do you notice? There's a what? Repetition or pattern. Good. So the idea we're going to talk about here is that one of them has repeating and one does not have repeating decimals. Okay, that's the easy way to think about it. And then we'll talk about how fractions are involved also. Worth?
Oh, could I give an example?
Sure.
Irrational?
Absolutely. Give me an example. Pi. Very good. And most people think of that right away. Pi is the easiest example. Pi goes on forever with no repetition, and there's no pattern that you can find. The number will go on and on forever, because what is pi really? Who can tell me the definition of pi? This is math theory now. What's the definition of pi? Very good. Well done. How would you say if I said use the word ratio and give me a definition? What would you say? It's the ratio of what? Yeah, keep going. Good, reverse, but yes, that's it. Pi is defined as the ratio of the circumference to the diameter. A long time ago, mathematicians said, you know what? Every time we're able to find the circumference around a circle and then find the diameter, when we divide them, we keep getting this number, 3.1415926, so it goes on and on forever. And they couldn't figure out what was going on there. So they defined this irrational constant, pi, and it's defined as the ratio of the circumference to the diameter. Again, that part not as important. The part that you're going to notice is that it goes on forever. Okay, and I'm going to put this little approximation symbol, 2 squigglies instead of an equal, because it's not really equal to, but it's approximately 3.14 ... with no pattern there. No pattern. On the next slide, there's going to be definitions of these, so you don't have to write the definitions down right now. Just listen for a little, okay? Rational numbers, as Georgia mentioned a minute ago, are easiest example are terminating decimals. But we can also have repeating decimals. So what's an example of a fraction that ends up to give you a repeating decimal?
2/3.
2/3. What is 2/3 as a decimal?
66.666.
Yeah, percent, or as a decimal, 0.66666 repeating. So this is all it is. 2/3 is really just 0.6 repeating. It is rational because of two reasons. Reason one, you can write it as a fraction. Whenever you can write it as a fraction with two integers, it's rational automatically. And some of you might say, well, I could put pi over 1, but pi is not an integer. Okay? And we'll talk about what integers are in a minute. So this can't be written as a fraction over here. 2/3 is a fraction. Whenever a number can be written as a fraction, it is rational. Always. That's the easiest definition. But the other way to look at it is to look at the decimal. Because there's a pattern that exists, it is rational. And you know what else? Use logic. If I said to you, in class today I had a student who was behaving irrationally. How would that student be behaving if they were behaving irrationally? Not normal. Out of the norm, right? Like they're like talking too much and they're like off the wall, they can't sit down. That's irrational. Irrational. You can't predict their behavior. You can't predict the decimals. Versus somebody that acts rationally, they act in a predictable manner. You could say like, oh yes, of course, they cross the street, it goes the light turn green. That is predictable, right? It is rational. Thus, predictable pattern. 0.6 repeating itself infinitely is predictable. You know that it's going to be 6, 6, 6, 6, 6 forever and ever. Now, what about terminating decimals, which is what Georgia said? Give me a fraction that, when reduced, becomes a terminating decimal. Terminating, Chris. 1/2. And what is that as a decimal? Good, 0.5. Now, you might say to yourself, well, this is terminating, so as Mr. Howell said a minute ago, sure, it's rational, but it's actually not terminating also. It's both terminating and repeating. Who can explain why? Why is this both considered to be a terminating decimal, or you can interpret it as a repeating decimal? Because I don't see anything repeating, so it sounds weird at first, right? I don't see anything repeating.
Because there's infinite zeros behind it?
Yes, exactly. Whenever you write a decimal out, so 0.5 is really 0.50000, and it goes on forever. Well, what goes on forever? The zeros do. So even though we say it's a terminating decimal, and you would still call this a terminating decimal, you can interpret it as a repeating decimal also. Okay? So again, anything that repeats as a decimal or terminates is rational. Anything written as a fraction is rational. Anything that is considered a ratio of two integers is rational. What's irrational? Things that have no pattern. That's the easiest way to remember. Can somebody give me another example of irrational? And not something like pi, not a constant. Something else they may have seen that has decimals that go on forever, but you can't figure out the pattern of it. It's a whole category of numbers, actually. Not just one number, but a whole category of numbers that are always irrational. Worth, I saw a hand.
No, I do know we have
Georgia?
Square roots. of
Good.
numbers.
That's exactly right. Square roots of non-perfect squares. What's the square root of 9, everybody?
3.
But what's the square root of 10? 3 point something, right? Those decimals go on forever, there's not going to be a pattern. Any square root of a non-perfect square. Okay? So the square root, and you can write underneath that radical symbol, of a non-perfect square. I abbreviated, you can write it out. A non-perfect square. Any perfect square obviously is rational because you could just take the square root of it. Any questions so far on rational versus irrational? Okay, good. Now, within the rational set of numbers, you can see we have 3 subcategories. The first of them is integers. Integers. What can my definition of integers be? Or maybe you could give me examples of integers that you may know. Okay.
Integers include all numbers on both sides of the number line, so
And-
negative and positive numbers.
Good. And what about those numbers? You need to give me more. There's one other piece of information you need to mention. Those numbers must be what kind of numbers? Good. So integers can be defined as whole numbers and their opposites. So write like this. Write a solution set notation. You can write a squiggly bracket. Forget the actual name. Anybody know the name of these brackets? Braces, that's probably it. Very good. I always forget that every year, and I always ask to see. So they're called a brace, and the way you would write this or draw this would really be like this. Okay, like that. That's what a brace looks like. I know, mine's a little ugly, sorry. That's what a brace would look like if you wrote it neatly, okay? So you open brace. You write ... -3, comma, -2, comma, -1, 0, 1, 2, 3, and close brace. I went over, sorry. But ... -3 all the way to +3, or -2 to +2. But put the ... dots at the end so you know that you're going for every whole number. Okay? And their opposite signs. Now that we've talked about integers, we know that they're positive, they're negative, and they're whole numbers. What's the difference between integers and whole numbers? Because they seem very similar, don't they? How can I classify? First name again? Tori May. Tori May, whole numbers. How would you classify it? Okay, good. They don't have a decimal, correct. What else? But integers don't have a decimal, so those look the same still. Good. Whole numbers are pretty much just like integers, but they're only positive, and you include 0. Okay? So it goes from 0 onward. So open brace, 0, comma 1, comma 2, comma 3, ... close brace. Again, whole numbers are just like integers, but you're not including the negative values. Now, the last one is one that, honestly, you're not going to see much of, but I'm going to go over the name of it. What is a natural number? Natural number.
So it's whole numbers minus 0.
Yeah, same as whole numbers, but don't include 0. What is another name for the natural numbers? There's another name that some textbooks might use that you may have heard of. The counting numbers. Okay, the reason they're called counting numbers, what do you start with?
1.
Yeah, you start with 1. You don't ever say, okay, 0, 1, 2. You don't start counting with 0, you count with 1. So the natural numbers may also be called the counting numbers. You're welcome to write that down if you'd like. It'll be on the next slide anyway, so don't worry. Okay? Any questions? Any questions? Let's go to our next slide and take a look at what these are defined as. You have some good examples here on the board, but in the next slide we're going to see some definitions, which you don't have to write down. I was nice enough to put it here for you. Can I get somebody to read for me, nice and loud? Nice and loud. Natalie.
Natural numbers, also called counting numbers. Think of where you begin counting objects.
Good. Go to the second one also, Natalie.
Whole numbers, similar to natural numbers, but with the inclusion of 0.
Okay, so now what am I doing here? We're working our way up. Remember earlier, we started with rational, we went to integers, we went to whole numbers, we went to natural numbers. By definition, we're going up instead this time, so we can see how they are all part of each other. Okay, does everybody know what a subset means when I used that word before? What did I mean when I said that the integers are a subset of rational numbers?
Oh, well, it's just not a category in the wrong.
Yeah, it's a category within a category. Very good. You know on your computer, when you make a folder within a folder, that's what a subset is. Okay? So I might have a folder that says Honors Algebra 2. And then within that folder, I might have notes, tests, quizzes. Those are subcategories, okay, or subsets. The third and fourth one, integers and rational numbers. Worth.
Okay. Integers, whole numbers and their opposites.
Well done.
Rational numbers, predictable decimals, can be written as a fraction or as a terminating or repeating decimal. Ratio of 2 integer values.
Good. And that's the one that we don't always talk about, but make sure you note that. It's a ratio, really. When you say fraction, fraction and ratio are the same thing. Okay? If I said it's a ratio of 1 to 3, it means it's really a fraction of 1/3. Okay? All right. So it's a ratio of 2 integer values, which is why earlier, remember we talked about how pi was irrational? Because pi is not an integer. So even if you say, well, pi can be written as a fraction, Mr. Howell, it looks like it can, but this numerator is not an integer. And our definition is integer values. So pi is irrational. And we could also think about it because it's unpredictable. So irrational numbers are unpredictable and have decimals that go on infinitely without a pattern. Any questions? Are we good on this? Good? All right. Next page. Number lines. Basic, very basic. This is how we learn how to count and do adding and subtracting when you're younger. So, number lines. The reason that they were introduced is because we needed a coordinate system. And this is a one-dimensional coordinate system. What coordinate system do you usually work with in math?
Two-dimensional.
Two-dimensional. How many axes?
2.
And what are they labeled?
X and Y.
Yeah, x and y. Now, we in math might start calling this axis the horizontal axis, and then we might call this one the vertical axis. Or you might call this the independent variable axis and the dependent variable axis. They're interchangeable, so we'll get through that kind of stuff too. But for today, we're just simply looking at number lines. So a number line, again, is a way to designate the location of a coordinate on the graph. Any questions on what a number line is? We're good? All right, cool. I know I'm going quickly. I don't usually go that quick, but with this topic, we can do that. Let's take a look at the first example. Find the coordinate of the point that is 2/3 of the way from A to B. Find the coordinate of the point that is 2/3 of the way from A to B. From A to B. Feel free to take a minute to try on your own, and I'll go through it. But think about what you have to do to figure this one out. I want a point that's 2/3 of the way from A to B. You can do trial and error. You can try points out and see which one works out to be 2/3 of the way. You can try doing it algebraically. You can try and do it in your head for a little while if you want. That's fine. Anybody have an idea on how we can start this problem? How can we start it, David?
Well, you find the difference between A and B.
Good. So let's start with that.
And then,
Hold on one second, okay? Everybody clear? We're going to start by finding the distance between them. Because if I want to know 2/3 of the distance from A to B, I need to know what the distance is. Okay? Now, Taylor May?
What?
Tori May, sorry. Do you want to answer this question? What's 2/3 of 6?
What?
What is 2/3 of 6?
4.
Yeah, very good. It's 4. How do you do 2/3 of 6?
If you have it on fractions, 2/3 equals x over 6, and then you multiply 3 times 2 is 6, and 2 times 2 is 4.
Good. So you set up a, what's the word?
Ratio. No. Proportion. Proportion.
So you can set up a proportion, or what else could you do? What does the word of mean in math? What is it? Multiply. Good, Chris. So you could just do this also. Okay? So you know that the distance should be 4, really, that you're looking for, right? Because that's what 2/3 of the full distance is. So it says from A to B. So start at A and count 4 spots over. Where do you end up? 2. That's your answer. Okay? There's your answer right there. So, and how can you check this? Who can tell me how to check this, please?
Well, you could just do like it backwards.
Good. So what's this distance here?
That's 4.
Good. And the other distance that's left over?
2.
Right? So this is 2 out of a total of 6. This is 4 out of a total of 6. So this checks out to be 2/3. This checks out to be 1/3, which total to be the full distance. Okay? So again, the full distance is 6. We want to go 2/3 of the way over. We go 4 units over, and that's at 2. How did I know to start at point A? How come I didn't go from B back to point A? How come I went in one direction and not the other? What reasoning might I have there? What reasoning?
It says to go from A to B.
Yeah, from A to B. Good. Make sure you read carefully. From A to B. If it said from B to A, then you would have started at B and you would have gone 4 units over, landing at 0. Okay? The next one is a lot more challenging. What I want you to do for this next one is to think about it first. Try and use your intuition and figure out the answer in your head. Okay, there's 2 answers for the next one. Try and figure out one of the answers in your head first. On the number line shown below, determine the coordinate or coordinates, that's what that parentheses means again, that are half as far from A as from B. Half as far from A as from B. Can I get 3 volunteers? 3 volunteers? 1, 2, 3, come on up. Yeah, come on. Okay, so Worth, you stand over here. Summer, stand over here, and Arthur. Okay, Arthur, what I want you to do is show everybody what would something be if you were half the distance between the two of them. Where would you stand? Okay, now what if it said that you were half as far from Summer as you are from Worth? Where would you move to?
Half as far from
Half as far from Summer as you are from Worth.
So if I'm like half as far from summer than I am from worth, so it'd be like,
Would you move closer to summer or closer to worth? This is what makes this problem tough, the wording behind it. You're half as far from summer as you are from worth.
oh,
You can help, Matt. You're all up here. It's fine. Tell them what to do.
yeah, it's closer to summer, so I'm
Very good. So now, what would the distance between the summer be? Estimate.
75% from like, I'd be a fourth closer to her than I would have
Third.
been.
You're close. Third, actually. Because this is going to be like, say if this is 2 feet, this would be 4 feet, right? It's
Well,
half
yeah,
as
now-
far, which makes it a third.
Yeah,
You see that?
Yeah.
Think about it for a second. Half as far. If this distance were 2 feet, what would this distance be? Half as far. 4, right? Because 2 is half of 4. If he is half as far from summer as he is from worth, that distance must be half of this distance. So what has he done? He's kind of broken it up into thirds. Right? If this is a distance of 2, and this is a distance of 4, that's a third of the way. This is 2/3 of the way. So you could start this problem by thinking about it that way with intuition. Thank you, ladies and gentlemen, for volunteering. But what we could also do, because that's one way to do it, we can solve it algebraically as well. Okay, we can solve algebraically as well. But we want to make some sort of a statement. The answer or answers that we're going to get are closer to A or closer to B? Closer to A or closer to B? Yeah, because it's half as far from A, right? As it is from B. So that we know already that somewhere around this area, that point is going to be landing. It's not going to be over here anywhere because that's closer to B. That's closer to B. So that means that there's some value in here somewhere and some value out here somewhere that may work. That may work. Somewhere. Yeah, absolutely. Take a good guess. Go ahead. One of them is -3. Very good. And that's the one that you can see. Most people can see that. And how can you see that? What is this distance here? What is this distance here? Isn't this half as far? 2 units away from A, 4 units away from B. Thus, it is half as far from A as it is from B. But what about that other number? What are we going to do to figure out that other number? And we can sit there and try numbers, and you can try them all day long. And if you did that, that's fine. But I want to know if anybody can think of an algebraic solution to do this. Remember, it's not just one coordinate, but there's actually another coordinate somewhere out here in space, beyond -5, to the left of -5, that exists in a fashion that it is half as far from A as it is from B. What number would that be? This is difficult, right? If we don't know something, what do we call it? X, or a variable. Very good. A variable. Some variable. So, shouldn't we just say some variable X for now? Do you already have the answer?
Oh, I have the answer.
Okay, hold on one second. Did you do it algebraically?
I just did in my head.
Okay, so hold on. We'll check at the end that you're right, but I want to do algebraic first. So what I want you to do is you either redraw the number line or just extend your number line. Okay, extend it to the left a little bit. Okay? Now, put a bunch of hash marks on here. Don't label them with numbers yet. And just call this X. We don't know where it is. We don't know what number it is, but call it X for now. All right? Now, the initial problem said it is half as far from A as it is from B. So we're going to need the distance from A, and we're going to need the distance from B. We're going to have to compare them to figure it out. If I were to ask you, what is the distance between B and A, how would you figure it out? Don't count. Tell me mathematically. The distance between B and A currently, how would you figure out? We know it's 6 by inspection, but how would you mathematically figure it out?
You could do 1 minus -5.
Perfect. So the larger number minus the smaller number. Okay. Is that clear so far? So if I want to know what the distance between A and X is, how would I write that as a variable, maybe, or as a variable expression? A minus X. Again, if I wanted to find the distance between B and A, I would do 1 minus the -5. But now I'm going between A and X. So the distance between A and X is A minus X. What is the distance between B and X? Between B and X. Georgia.
Never mind. I don't know.
Oh, you had your hand up.
I know. I was.
Help her out, Tori.
A minus 2x? Oh wait, no.
The distance between B and X, though. Not A. Now we're not even on A anymore. How did we figure it out, the distance between A and X?
It would be A minus x.
It was just B minus A.
Okay, I see what so what Tori May is doing is she's breaking it up into pieces and saying it's whatever this distance is that we got plus this gap here, right? This 6-point gap. But if I wanted to write it as a variable, how can I continue with the pattern that we're using here? Hannah, right?
Yeah, B minus X.
B minus X. So, Tori May, what you said is absolutely right. You can do that. You can break it into these two pieces and put them together. But what this does is it makes it easier for us. Now,
And then do you make the solution set and then, okay.
do anybody have a suggestion as to what we can do now? Because we know the distances in variables. We can plug in for A and B. We still don't know what X is. But we know a relationship between them. We know a relationship. How much should the distances be when you relate them to each other? Which is bigger? And by how much? By what ratio? Hint, ratio.
Well, you could like make it so it's like 2 and then in parentheses A minus X equals B minus X.
Yeah, why would you do that? Because you know it's...
Half of the distance.
Since this distance, A minus X, we said is half, right? Remember this distance here between A and the answer is half of the other one. She's saying put a 2 in front of here because this was half of this. Again, I'll put it on here. This was half of this. Because of that, you could put a 2 in front and set them equal. That's one way of doing it, absolutely. And that's probably easier than what I'm going to show you. But I want to show you just the other way because it's a proportion. You could also do this. You could also say that the ratio of A minus X over B minus X is 1/2. And think about that logically for a minute. The 1 is representative of this distance. The 2 is representing this distance. And we said a minute ago that the distance from A is half of the distance from B. So you could also do that. But Tori May, what do you notice? What's going to happen if I cross multiply? What are you going to get back to? Yeah, the same thing she said a minute ago. Cross multiply. You have to put the 2 out front here, and this goes in parentheses. And then when you take the B minus X here, you're going to get back up to this equation.
Plug in what B and A are.
Exactly, and you can solve for X. So let's cross multiply. Remember, please, to put parentheses here. Cross multiply. 2 parentheses A minus X equals B minus X, giving us the exact equation that Tori May thought of a little while ago. You can plug in for A and B. What is A in this problem again? What coordinate is A located at? What is it? -5. What is B? 1. So plug in, please. Solve the equation. What do you get for X when you solve this? Did it work? Did it get the same answer you got?
I have to do it over it, so yeah, I get an so -11.
Very good. Very good. Well done. -11. Okay? Now, you're going to be like, how is this true? How does -11 happen to be half the distance from one as the other? Go back to your number line and check. Item.
A is 6, turn it to A, and B is 12.
Yeah. If you plot this with -11, I go all the way back to the top up here, and I extend this a little bit, and I go all the way out to -11. This distance here will be 6. This distance here will be 12. 6 and 12 reduced to a ratio of 1/2. Again, half the distance away. So this is an interesting problem, right? You see how it makes you think outside the box? Because right away it's like number lines, those are easy, that's cake. I could do that sleeping. But when you start thinking about problems like this, you're like, all right, now I got to really start thinking. This is an example of a high-level SAT problem. On the SAT, there's easy, medium, and difficult. This would most definitely be considered a difficult problem because there's a good chance they would say, find the 2 coordinates that fulfill this whatever, or find one of the 2 coordinates, and you could have to grid it in. Okay, the 3 might be easy that we got earlier, or -3 rather, for our first answer, but the -11 is a lot tougher. Okay. Let's see. Let's talk about one other thing before we dismiss. Inequalities in number lines. Who can tell me what an inequality really is? And I don't want to read that off the board, but what is inequality to you? What does it do for you? Because an equality makes an equation, right? What's an inequality? What does it do? Yeah, tell you something is less than or greater than. David is taller than I am. His height is greater than my height. Agreed? Absolutely. I'm jealous. I'm very jealous of this. I wish I was taller. But that's comparison, right? And you can compare 3 people. You could say person A is taller than person B, who's taller than person C, etc., etc. Here's what you do. Tonight, the video is recorded. All I want you to do is watch from example 3 to the end. Okay? The last part from example 3 is not that long. You're going to see there's an example to do here, and then I talk about absolute value for a little bit. Okay, I know we lost some time with the textbooks, or else we would have easily finished. So tonight, watch from this point on, finish taking the notes, and then you'll see there's a homework section. I'll put the homework on Moodle, but it's also the end of your notes, and that is right here. Okay? So the homework is there. So tomorrow, we have class tomorrow already, all right? We're off on day 6 in this section. So tomorrow, you should have watched the rest of the video, and it's not long, it'll probably be like 4 minutes or so only, and then work on these problems. Clear?
In the textbook?
On Moodle, I'm going to post a video under Mr. Howell's math videos that I record on my own, and it'll be about 17 minutes long. You don't have to watch the whole thing. Skip to example 4 and just watch just like the last 4 minutes. Okay? You can do your homework on Notability right after your notes by adding another page. For those of you that want to be neat, you can do your homework right on here after your notes if you would like to and show it to me. That's fine that way. Or you can do it on paper. Either way is fine for tomorrow. Okay, again, leave a book at home, leave one in school. If you didn't get a book yet, hang out for a minute.